Welcome to SMALLab, an embodied learning environment. SMALLab is a platform where physical action meets targeted learning. There are two goals in this 2-day-long scenario. The first is to allow students to experience centripetal force kinesthetically with body movements. The second is to instruct and reify the concept that objects that are released from centripetal force travel in a tangent at the point of release. And we're going to be teaching you how to teach your students about centripetal force and the 3 variables that affect it. So those variables are mass, which will be the amount of matter inside this ball, radius, which is the length of this string, and velocity, which is how fast this object is swung. Here's an example of how I can adjust velocity with this handheld object that's being tracked. Today is also, this first day of the lesson, is a good time to remind your students that there's no such thing as centrifugal force. On day 2, you're going to be using this releasable object. There's 2 components. There's a spring lever release here that when I push it, releases this part that's being tracked as it flies off, while the handheld object is also being tracked. And so they'll have to physically spin their bodies, rotate their bodies, and then they'll release the object and discuss the trajectory after release, how that flows. So this is day 1 of your centripetal force lesson, and we're going to be using this tethered object. The first thing you'll want to do is get them to understand or talk about the tracking and the mapping that's happening. So this handheld part here maps to the yellow ball that's close to the plus sign. And then as you swing it, you'll see that the tennis ball that's swinging around maps to the green ball that's moving. Coming out of that green moving ball are 2 vectors, one that's pinkish and coming straight out at a tangent, and that represents the tangent at that instant. And the other one is a yellow vector that's heading towards the plus sign, and that represents centripetal force. In this case, centripetal force is the tension coming from the string. There are several different ways to swing this object. Often when the kids first come out, they'll swing it sort of tentatively like this, but if you encourage them to hold it overhead, they can really get a good swing in there and get some real velocity going. Really watch the arrows get bigger and smaller, and also feel it in their arms in a very embodied way, how difficult or how easy it is to swing it. They can really feel centripetal force working on the string. The string is the tension that represents centripetal force. So now we'll talk about the 3 variables. The first one is mass. And this nifty tennis ball opens up, and you're able to insert packets of varying mass inside it. So I'm going to take this second packet, about 90 grams in there, and insert it into the tennis ball, and then close it back up. And now when I try to swing this object, I can actually really feel how much harder it is to get it swinging. There's a lot more centripetal force at work here, and I really can instantiate that in my arm and in my body. The next variable we're going to discuss, or let your students explore, is radius. And so that is represented by the length of the string. So here we have a quite long string. The radius is going to be long. In the equation for centripetal force, radius is the denominator. So if I make this string shorter, then is it going to be harder or easier for me to swing it? Let's see what that looks like first. I can push this down. Now the string is shorter, and I can tell you that it's actually harder to get it swinging around. So because the radius is decreased, the centripetal force has increased. The third variable that you'll want to explore with your students is velocity. And so that's the speed and direction with which you swing this tethered object. So right now I'm trying to do a pretty low velocity, low, slow, constant velocity. And you can see the vectors are not so large. But now when I really give it a good spin, I really feel how much harder it's tugging on my hand. Centripetal force is increased. You can see that by the vectors on the ground. And I can really feel it as well. I'm experiencing it. So now you'll be nearing the end of day 1. You've gone through the 3 variables. You might throughout the day want to talk to your students about what are some real world phenomena that you see that are affected by centripetal force. And you probably have experienced some of these, being on a roller coaster, going through a loop, merry-go-rounds, figure skaters that are spinning around one another, holding arms, discus throwers. Also, the students like to come in the space and just explore how the tracking works with the dotted pathway. And so they could try to make an infinity sign or a perfect circle. We want them to be comfortable, get comfortable in the space, and to explore those 3 variables. And again, each student needs to do something different with each variable so they can really embody it themselves and feel it, feel the difference when they change the mass, etc. On day 2, you'll be ready to talk to them about the trajectory of an object released from centripetal force. What you want them to do before you actually show them is spin around and have them predict where they think the ball is going to land. So for instance, you might say to them, I'm going to release the ball when I'm here. Where do you think it's going to land? At that corner, that midway point, or the furthest corner? And then you'll do it and see where it lands if they were correct. Once your students have understood the concept of the point of release and velocity and how those variables interact for where the object's going to land, you can play a game with them by placing a target on the ground and then having students come up and spin and try to hit the target. Now, anything over a foot in diameter is probably going to work fine, and you have to make sure that they spin at least twice. That makes the game more fun. So, call on a student or split them into teams, have them come up, spin, 1, 2, and release. Your students won't always be perfect at hitting the target the first time, and so you want to turn that into a teachable moment. So remember, they have to spin twice, once and twice, and then if they miss the target, discuss with them what they could have altered to hit the target. So in a scenario like this, we know that it's a straight tangent, and perhaps they should have released later to try to hit the target over here. One of the really fun things that we like to do with students is have them hit a moving target. So ask some intrepid student to take the target and move across the space. So I'm spinning while the student is moving, and now I've got to hit this moving target. I think that would have been a hit. Circular motion and the trajectory of release is a common misconception. We gave this item from the FCI to 17 high school students who were halfway through their physics course. At that point, only 47% got it correct. After 2 short sessions in SMALLab, we regave the test, and now 89%, a statistically significant increase, got it correct.